Okay, today we are starting our pre-calculus notes with 1.1 on basic operations with matrices. This here is what a matrix looks like. What it is a rectangular array of numbers consisting of rows and columns. So first let's talk about what the dimension of a matrix is. So I'm looking at this matrix here. We always say the dimension is row by column. And this one here happens to have 2 rows and 3 columns. Each index inside, or the elements inside here, can be designated with 2 indexes, I and J. The I is for the row, the J is for the column. So I'm saying, okay, what element is represented by A sub 2, 3? That's row 2, column 3. I go to row 2, column 3, see where they intersect, and I would get an 8. Next one's asking, okay, what element is for row 1, column 4? So we look at row 1, column 4, and that would bring me to the element number 10. We do have what is known as a zero matrix, and that is any matrix whose all the elements are zeros. A square matrix is a matrix whose number of rows equals the number of columns. And an equal matrix are matrices with the same dimensions and corresponding elements are equal. So let's take a look at that concept here. It's asking me to solve the variables here for x and y. So I'm looking where my x variable is. I'm in row 1, column 1, so I'm going to correspond that, put that equal to the element in the same position, row 1, column 1. So 2x is equal to 8, divide everything through by 2, we get x is equal to 4. To solve for y, I see I'm in row 2, column 1, so I'm going to look at row 2, column 1. So negative 9 is equal to 3y, and therefore y would be equal to negative 3. It's fine if we have multiple sets of matrices here. The same concept's going to happen. I'm looking for the x's, and I see that each of the x terms is in row 1, column 1, so that means I'm going to use the other element that's in row 1, column 1. So we're just going to set this up exactly like we see it. Negative 6x plus x squared is equal to negative 8. It is a quadratic, so we do need to have everything over to one side. And this is factorable. So you have x and 4 and 2, they're both negative. So x here is equal to 4, and x is equal to 2. It is okay to get multiple answers. Now let's look at the y. So the y is here and here, and I can see that's row 2, column 2, row 2, column 2, so I'm going to use that same element here as I set up the equation. So 5y squared plus 7 will equal 10y plus 7. Our 7's cancel. Again, we're looking at a quadratic. We need to set it equal to 0. This is factorable. We can factor out a common term of 5y, leaving you with y minus 2. And our 2y values here would be 0 and 2 once you set them equal to 0. We could do some basic operations with our matrices. So let's first talk about adding and subtracting. In order to do so, the matrices must have the same dimension. Otherwise, the operation is considered null. If the operation is defined, meaning they have the same dimensions, all the elements that are corresponding will be added or subtracted to produce the new matrix. So I'm given matrices A and B. I can see each of these are a 2 by 3 matrix. Since they have the same dimensions, they can be added together. Our resulting matrix will also be a 2 by 3. And we're just going to add elements in the same position together. So we're going to get 14, then we'll get 2, negative 7, and then just kind of continuing on, here we get negative 8, 3, and 4. Okay, so if I'm looking at this here, I want to subtract b from a. Make sure you're going in the correct direction. So we're going to take the element here and then subtract the corresponding element over here in matrix A. Again, the dimensions are the same, so the answer will also be a 2 by 3. So 9 minus 5 would get you 4. 0 minus 2 would get you negative 2. Negative 7 minus 0, negative 7. And then continuing on to the bottom row, we would get negative 22, 5, and negative 2. All right, moving on to scalar multiplication. That looks very much like the distributive property that we are familiar with. A scalar really just means any real number. So any real number. So in this case, our scalar here is negative 5. All you need to do is multiply this negative 5 to every element inside the matrix, no matter how big the matrix is. So we're going to multiply each element. So in this case, as we multiply in, we're starting with a 2 by 2. We're going to end by a 2 by 2. We're going to get negative 15, 15, 5, and negative 20. Okay, let's look at the next page. All right. So we're still multiplying by a scalar here. It's telling me to take matrix A, always designated with a capital letter, and multiply it by 1/3. So each of the 6 elements sitting inside matrix A will be multiplied by 1/3. Since this is a 2 by 3, my resulting matrix will also be a 2 by 3. We'll have 5/3, 2/3, 0, 7/3, negative 1/3, and 1. Now problem B is a little bit different. Matrices will follow PEMDAS. So first thing I'm going to do is the scalar multiplications. First thing I'm going to do is take matrix A and multiply it by 4. So each of these elements will be multiplied by 4. And that will result in 28, 0, 28, negative 4, and 12. Now I'm going to take this as a negative 2 and change it to a plus. I'm going to multiply negative 2 into all of these elements inside matrix B. And that's going to result in negative 18, 8, excuse me, not 8, 0, I was copying from the wrong place, 14, 30, negative 8, negative 2. The reason I like to distribute the negative in is because in that case I don't have to worry about having to remember to subtract through. Now we're going to combine these two guys together, and we will get 2, 8, 14, 58, negative 12, and 10. Okay, so let's continue on here. A little bit out of order, which is fine. I just want to make sure we understand that matrix multiplication is different from scalar multiplication. And I'll get back up to this column and row situation that we have here. So let's say we have matrix A, and matrix A is an m by n. And it's telling me that matrix B is an n by p. If we're going to be able to multiply these matrices together, the columns in A must match the row in matrix B. If they do, the resulting matrix will be what these outside terms are. So this would be an m by p matrix. All right, so let's apply that right up here to this guy here. This is a 1 by 3. This is a 3 by 1. The rows in A match the columns in B. Therefore, a resulting matrix is just going to be a 1 by 1. So if you have a row and a column with the same number of elements, you are just going to get a single answer. And what you do is you start with the first element in the row and the column. We multiply those two guys together. Here we move left 1, here we move down 1, and then we multiply those next two together. So negative 2 and 4 would get us negative 8. Move to the left, move down. 1 times 8 would get 8. These guys get canceled, and our resulting matrix is singular at -15. Okay. So what happens if they don't match? If the number of columns must match the number of rows, just like we said before, otherwise AB is not defined. So you can just say undefined. So let's continue on looking to see, are these matrices capable of being multiplied together? So I'm looking here, we got A is a 2 by 5, B is a 5 by 4. The columns in A match the rows in B, and our resulting matrix is going to be what this outside piece is, so we're going to wind up with a 2 by 4 matrix. Looking at problem B, 3 by 2, 4 by 3, the columns in A do not match the rows in B, so this one would be undefined. Alright, so let's just take a look at these two here. Matrix A is a 2 by 3. Remember, we go row by column. B is a 3 by 2. So if I want to multiply A to B, and order is important, you're going to have to list them in the correct order. So I'm listing the dimensions of A first, then B. The columns in A match the row in B, and my resulting matrix is going to be a 2 by 2. If I go in the other order, B, A, so I'm going to list the dimensions of B first, and then A. This again is still defined because the columns of B match the rows in A, but a resulting matrix would be a 3 by 3, which makes matrix multiplication different than real number multiplication because it is not commutative. So this is really important. Matrix multiplication is not commutative. Alright? So it's going to be really important that you follow the order because you can get different answers when we're dealing with the matrices. Alright, so let's just finish this up by multiplying a couple of matrices. So I'm looking at this first one here. Again, we have a 2 by 2 by a 2 by 2. These match. Our resulting matrix will also be a 2 by 2. What I like to do is set up a work matrix and then a final answer matrix. So we're looking at this here. I need to fill this spot here, which is row 1, column 1. So I'm going to pull from row 1 and column 1. I'm going to start with the first elements and multiply them together, then move to the left one and down one. 6 times -3 would get us -18, and you're going to wind up with -6 in that first position there. Okay, so then I'm looking at this next spot here, which is row 1, column 2. So I'm going to pull from row 1 and column 2. Start with the first two elements, so 3 times 2 is 6. Moving to the left and then straight down, 6 times 8 is 48. So the element here will be 54. Then looking at our next position, I'm looking to fill spot in row 2, column 1. So I'm going to use row 2 and column 1. Starting with the first elements in those rows and columns, we get 28. Moving to the right and then down. I said left before, to the right, sorry guys. And then we're going to have -1 times -3, which is 3, so we'll get 31 here. And lastly, we're looking at row 2, column 2, so row 2, column 2, so we use row 2 and column 2. Starting with the first elements, we get 14. Move to the right and move down, we get -8, so we would get a total of 6 there. Alright, so let's see if B is first of all defined. So this is a 3 by 2. This is a 2 by 3. Columns match the rows. It's a 2 by 2, not a 2 by 3. Our resulting matrix is going to be what's on the outside here, which is a 3 by 2, so we're going to have 6 spots to fill. There's my work matrix, and then my final answer will be put there. So right here, we're looking at row 1, column 1, so I'm going to use row 1 and column 1. Multiplying the first elements, you get -3. Moving to the right and down to pull the next set, you would get -5. So our answer here would be -8. This position here is row 1, column 2, so we're using row 1 and column 2. Starting with the first elements, we'll get 18. Moving to the right and then moving down, you get -4, so you get 14 there. Over here, we are looking at row 2, column 1, so we use row 2 and column 1. Starting with the first elements, we get +3. Moving to the right and down 1, we get 30 there. So when we combine those up, we get 33. This position here is row 2, column 2. So again, we're going to row 2 and column 2 is where we're pulling from. Start with the first elements in each. -18, shift to the right and down 1, multiply those two guys together, 24. We get a total of 6. We have 2 more positions to fill. So now we're looking at row 3, column 1, so we're going to use row 3 and column 1. Starting with the first elements, we just kind of repeat the pattern. Get +6, moving to the right and down 1, -30, so we'll get -24 in that position. And lastly, we are looking at row 3, column 2. So I'm going to use this column with row 3. Multiplying the first elements together, you get -36. Shifting right and down, we get -24, and that totals to -60. All right, let's see first of all, is it defined? Here we have a 2×3 multiplied to a 2×3. The columns in A do not match the rows in B, so this one here is undefined. This cannot be multiplied. They could be added because they have the same dimensions, or subtracted, but they cannot be multiplied. Okay, with that we conclude our first lesson in pre-calc, and I'll check back in with you next time.